In this presentation, let us discuss about the construction of the character table for C2v point group. So in the previous presentation, we had already gone through great orthogonality theorem and its applications. So the mathematical statement of the theorem was discussed, and out of that, 5 rules were derived, which, as it was said, going to help for the constructions of the character table. So a recap of all the 5 rules is been given here. So what is that? So number of irreducible representations in a group will be equivalent to number of class in a group. The sum of the squares of the dimensions of a representation will be equivalent to the order of the group. The sum of the squares of the characters of any irreducible representation will be again equal to the order of the group. Then the characters of two different irreducible representations are orthogonal. So these are the various rules, and also the characters of all the matrices belonging to the operations of the same class will remain identical. So these are the rules that was actually discussed in the previous presentation, and we are going to make use of these rules for the constructions of the character table for C2v point group. So as we are aware that for C2v, C2v point group, so it has 4 symmetry operations. So 4 symmetry operations. So what are those 4 symmetry operations? Let us see. Okay, so they are E, C2, sigma V XZ, sigma V YZ. So these are the 4 symmetry operations which could be found in C2v point group. Now let us go ahead with the calculations of the constructions of the character table step by step. So the first step, according to rule 1, the number of irreducible representation. So here comes the number of irreducible representation will be equal to the number of class in a group. Okay, so this is the first rule. So in C2v, as we said, 4 symmetry operations are there. So they are E, C2, sigma V XZ, sigma V YZ. And for C2, the number of class, okay, so that will be equivalent to 4. Again, what are they? So 4 classes are the same symmetry operations here. So here we represent C2v in this table, and 4 symmetry operations, otherwise the 4 different classes E, C2, sigma V XZ, sigma V YZ listed over here. As per rule 1, number of irreducible representation is equal to number of classes. So since 4 classes are there, since it contains 4 classes, okay, since it contains 4 classes, so it will be having it will have 4 irreducible representations. Okay, 4 irreducible representations which are represented as irreducible representation 1, 2, 3, and then 4. Okay, so here we could represent that 1, irreducible representation 2, irreducible representation 3, and irreducible representation 4. So this is the first rule. Okay, then what about the second rule? So what is the second rule? So second rule states that the sum of the squares of the dimensions, the sum of the squares of the dimensions of the representation should be equivalent to what? H. What is H here? Order. So in C2v, what is the order? Order, it is number of the symmetry operations. So here the number of symmetry operations, how many? 1, 2, 3 and then 4. So the order will be 4. Okay. Now let us see. The sum of the squares of the dimensions of the representation is equal to the order of the group. So let the dimensions be, or let the characters, let me tell, or let me say that the characters, the characters of E are called dimensions, Okay, so if that is the case, then we could label as 4 characters of E representation will be L1, L2, L3 and L4. So these are all the the characters of the representation E. So here, let us just write here L1, L2, L3, L4. So here why it is said so? Why? Because these are the dimensions of the representation. So the characters of E identity will be called as, or will be said as, the dimension of the representation. So when we consider the second rule, the sum of the squares of the dimensions will be equivalent to the order of the group. So for which we are just considering the dimensions to be L1, L2, L3 and then L4. Now according to that rule, we are going to square each and then sum up. L1 square plus L2 square plus L3 square plus L4 square is equal to the order of the group. Here order should be 4. So that is the H value. So this is satisfied only by 4 one-dimensional representation. So 1 square plus 1 square plus 1 square plus 1 square. Then that will be equal to what? 4. So this is satisfied, okay, only by considering by 4 one-dimensional representation. Okay, so here instead of that L1, L2, L3, L4, let us write the values that we have evaluated using the second rule. Sigma V X Z. Once again, let us repeat sigma V Y Z. Then irreducible representation 1, 2, 3 and then 4. And we have evaluated for L1, L2, L3, L4 to be one dimensional. Now what we are going to do, let us consider the unknown. We are going to apply, or we are going to evaluate the other things. So the unknown, the next step, let us consider the unknown characters, okay, for all the irreducible representation, okay, all the irreducible representation can be considered can be considered as follows. So here for first irreducible representation, the unknown characters, let it be A1, B1, C1. The next for the second one, A2, B2, and then C2. So likewise, I am going to consider the unknown characters by these labeling. So E, C2, sigma V, XZ, sigma V, YZ, 1, 2, 3, and then 4 irreducible representation. And we have evaluated the dimensions to be one-dimensional representation. Unknown characters are labeled as A1, B1, C1, A2, B2, C2, A3, okay, B3, C3, and A4, B4, C4. Okay. Now, what is the next step? We are going to evaluate the unknown characters. Okay, now what is the third rule? So, what is the third rule? Third rule says that the sum of the characters of or any irreducible representation should be equal to the order of the group. The sum of the characters of any irreducible representation should be equal to the order of the group. So, what we are going to do now? So, let us consider. So here we are going to consider any irreducible representation. In this case, the first irreducible representation, let us take up. And the sum of the characters of any irreducible representation should be equivalent to, that is, sum of the squares of the characters should be equivalent to what? The order. So in this case, we are going to do that. So according to the third rule, the sum of the squares, the sum of the squares of the characters, the sum of the squares of the characters in any irreducible representation, it should be equivalent to what? H. Okay. So what are those irreducible representation? The first irreducible representation, we have 1, so 1 square plus A1 square plus B1 square plus C1 square, and that should be equivalent to what? 4. So how come this will be satisfied? If this will be satisfied, the result 4 you will be getting only if you are considering A1 is equal to 1, B1 is equal to 1, and then C1 equals 1. So finally, we are going to have, or we have evaluated that to be, so here once again, C2v, E, C2, sigma V, XZ, sigma V, YZ. Okay, so irreducible representations are written here. Then this was evaluated one-dimensional. Now we have evaluated the first row, that is the first irreducible representation characters, that is 1, 1, 1. And to make a note, we could say that for any point group, there should be one irreducible representation which is symmetrical to all the operations, okay, which is symmetrical to all the operations. That means the characters corresponding to all the operations must be +1. So the first irreducible representation, we could see that is for the first one, we could see it is 1, comma 1, comma 1, comma 1. So this is what we have evaluated for the first irreducible representation. Next, let us evaluate for the other irreducible representations. Okay, so how to do that? Let us see. So here comes C2v E C2 sigma v xz sigma v yz. Okay. Okay. Then here we have already assigned this to be A2, B2, C2, A3, B3, C3, A4, B4 and C4. So likewise, we are going to evaluate for other. So here this we have evaluated 1, 1, 1 and over here it is 1, 1. So we are going to find the characters over this. So for which we are going to make use of the fourth rule. What is the fourth rule? According to that, orthogonality theorem. So orthogonality theorem must be satisfied by all the symmetry operations. Okay, orthogonality theorem must be satisfied by all the symmetry operations. Okay, by all the symmetry operations. So what is that actually we have said there in the fourth rule? What is fourth rule? So fourth rule, the characters of any two irreducible representations are orthogonal. So in that case, what we are going to do here? So summation over R, okay, the irreducible representation, that is the character of any symmetry operation belonging to ith group into the symmetry element or the character belonging to a similar same group but different irreducible representation. Then if we just take the product, then it should be equivalent to what? 0. Why? Because they are orthogonal with each other. So I is not equal to what? J. This is the condition. So in that case, I am going to take two different irreducible representation and I am going to take the product of the two irreducible, that is the product of the characters of the symmetry elements of two different irreducible representation, then it will be resulting into what? 0. Then that should be equal to 0. So in that case, I am going to consider, so this one, irreducible representation 1 and irreducible representation 2. So if I am considering 1 and 2, that is 1 and 2. For this one, what do I get? So irreducible representation 1 value is this one. And what about second irreducible representation, this one? So it will be 1 dot 1 plus other symmetry operations are there whose characters we have to take into account. So here it is A2, B2, C2. So the next we need to take the product of the character of the next symmetry operations of two different irreducible representations. So that will be 1 dot or 1 into 8 plus 1 into B2 plus 1 into C2, and it is obeying orthogonality theorem. So it should be 0. The integral should be 0. Now in this case, how it will become 0? Now let us consider A2 to be 1, B2 to be -1 and C2 to be -1. If that is the case, then we get 1 into 1 plus 1 into 1 minus 1 into minus 1, that is minus 1. C2 is minus 1, so 1 into minus 1, it will be minus 1. So all will be cancelling, then we get what? 0. Therefore, the third irreducible representation, we are getting 1 comma, sorry, this is, we are evaluating for the second irreducible representation. We are getting 1, then 1, then minus 1, minus 1. So this is what we are getting. So A2, we are substituting with 1, and B2, we are substituting with minus 1, minus, and C2, minus 1. Remaining we have here B3, sorry, this is A3, B3, and C3. Similar, this is A4, B4, and C4. So let us do the same way for other representations as well. Then we will be getting the values for the characters for the other unknown values. Okay, so here let us consider the next one. For irreducible, we are going to evaluate the third irreducible representation. So here, third one, so it is considered with along with the first one. So third irreducible representation and first. So if we are taking, then what is that we get it? So third one, it is again 1.1. So here the third one 1.1, then A3.1, B3 dot minus 1. Sorry, this is irreducible representation 2. Nothing wrong that if you do that also, but for simplicity we will take up the first one. So 1.1, A3 into 1, B3 into 1, C3 into 1. So if you do that, 1.1 plus A3 into 1 plus B3 into 1 plus C3 into 1, and that should result into 0. Now let us take, let A3 is equal to, in this case now minus 1, B3 is equal to minus 1, and C3 will be equivalent to, okay, so in this case B3 let us consider 1 and C3 should be minus 1. You can consider any way, but later when we are consolidating in a character table, the sequence should come in this way for assigning the Mulliken symbol in a sequential manner. So let us consider A3 to be minus 1, B3 to be 1, and C3 to be minus 1. Now what you get it? So here we have evaluated. Similarly, so the third one we have evaluated to be 1 minus 1, 1 minus 1. Okay, so next we are going to consider the fourth one, okay, into the second. That is the first one. So we are going to evaluate for the fourth irreducible representation. So 1 into 1 plus A4 into 1. So here we are going to evaluate this one. So 1 into 1. So 1 into A4, 1 into B4, 1 into C4. So what is that you will be getting? Let us see. Plus B4 into 1 plus C4 into 1 equals to 0. So this is possible only when A4 is equal to minus 1, B4 is equal to minus 1, and C4 will be equivalent to what? Plus 1. Okay, in that case, irreducible representation 4 product of these two will become what? 0. So finally, what we do, what we have got, so we have got the answer to be, okay, we'll summarize here finally. So C2, okay, C2v point group. So E C2 sigma v xz sigma v yz. Symmetry elements, 4 classes, order will be the 4, and 4 irreducible representation, okay. And for the first irreducible representation, all are symmetric with respect to the symmetry operation. So all are 1, 1, 1. And all are one-dimensional representations. So under E, characters are all 1. Then the second one, what have you evaluated? For second, it will be 1, 1, minus 1, minus 1. So let us write there 1, 1. Okay, so, okay, 1, 1, minus 1, minus 1. Okay, the third one, 1, minus 1, 1, minus 1. So 1, minus 1, 1, minus 1. And the fourth one we have got as minus 1, minus 1. Sorry, the fourth one it is 1, minus 1, minus 1, 1. So let us write here 1, minus 1, minus 1, and then 1. So far we have seen how in what way we have obtained the characters of all the symmetry operations by applying all the rules of the great orthogonality theorem. Now we are going to derive the Mulliken symbol. Now let us assign the Mulliken symbols for the irreducible representation. So this is how we have constructed. We have got the characters for the symmetry operations for each irreducible representations. Now let us just assign the symbols for the irreducible representation for which the rules have to be followed. So one dimensional, if it is a one dimensional representation, then you need to give the symbol A or B. Okay, so A or B need to be assigned if it is one dimensional. If it is two dimensional, then it will be E. If it is three dimensional, it will be T. So in our case, in C2v, it is A or B. So that we have decided. The next aspect is if it is one dimensional, then that one dimensional irreducible representation should be symmetric with respect to what? Okay, it should be symmetric. Okay, if it is symmetric means it should be plus 1. Okay, with respect to principal axis. Okay, principal axis, otherwise subsidiary axis. If it is symmetric with respect to principal axis, that is Cn, then it is assigned A. Okay, then that will be assigned the term A. And if it is antisymmetric, okay, that is minus 1, then it is assigned with the symbol P. So this is how it is done. The next, so let us see with these first two, it is one dimensional, so it should be A or B, A or B. And again here also A, B, here also A or B, here also A or B. Now what about the next one? It is symmetric, that is plus 1 with respect to the principal axis, that is Cn. Which is the principal axis? This is the one, Cn. So with respect to that, if it is 1, then what is the symbol? It has to get A. If it is again plus 1 here, then here we are getting A. If it is antisymmetric minus 1, it will be B. Minus 1, it will be B. So we have assigned. Okay. So the next, what is that we have to see? The one-dimensional is, that is one-dimensional representation, irreducible representation is symmetric. Okay. Symmetric plus 1 with respect to what? Sigma V. With respect to sigma V. Okay. That is vertical plane of symmetry or subsidiary axis. Okay. Then we get the subscript. Okay. Subscript should be 1. If it is antisymmetric, okay, if it is antisymmetric, minus 1, then we get the subscript 2. Okay, so that the subscript will be 2. Okay, that will be 2. Again, I am repeating the one-dimensional irreducible representation if it is symmetric plus 1 with respect to sigma V or subsidiary axis. In case subsidiary axes are present other than principal axis, the C2 axis are said to be subsidiary axis. If that is the case, the subscript 1 has to be assigned. If it is antisymmetric, subscript 2 has to be assigned. So in our case, so this sigma B is considered vertical plane of symmetry, which is plus 1. So A1, again minus 1. It is minus 1 means subscript 2 has to be given. B plus 1. Okay, then B minus 1, it is 2. So this is how the Mulliken symbols have been assigned in the character table. So finally, the character table can be further on performing symmetry operations on basic vectors. Okay, so we will be getting a complete character table for C2v point group. That is the actual character table for C2v point group. So finally, on performing the symmetry operations, okay, on the vector symmetry operations on the vectors, that is x, y, and z translational vectors, then binary products x, y, y, z, zx, otherwise the squares of the vectors such as x square, y square, z square. So, or otherwise the rotational vector, atomic orbital. So these are all said to be the basis over which the symmetry operations have been performed, and we get the results, the characters. So that actually summarized against each linear operation functions or binary functions or quadratic functions, which are actually mapped over here, and that the topic is separately dealt actually, but here we are going to write it, summarize it. Later stage we will be knowing how we are mapping or how we are getting the characters for these base vectors, okay, various vectors by performing symmetry operations. But here just we'll be writing whatever the result we have obtained, okay, the characters of various symmetry operations against the irreducible representation. Then here it will be 1, minus 1, minus 1, then minus 1, 1, minus 1. So here it will be minus 1, minus 1, and 1. And Mulliken symbol, as it was discussed, it is A1, A2, B1, and B2. A1, A2, B1, B2. Okay, so here for various linear binary functions and rotation functions, these are the operators, these are the characters which have been obtained for the symmetry operations. So for TZ, that is Z, we will be getting this symmetric character 1 1 1 1. Okay, and similarly for or z rotation along z axis, we get this, and here it will be x r y, then here it is y r x, and here quadratic functions x square y square z square. So here these are all used when we go for the applications, when we find the fundamental modes of vibrations, that is IR and Raman active modes, for which we will be using these linear functions, quadratic functions variables x z y z. Okay, so this is what the character table for C2v point group. So C2v point group, if you want to categorize, so this will be considered to be area 1, which is having what? The characters. Which one? The characters of symmetry operations. The characters of symmetry operations. Okay, so that is, we could separately or we could distinguish various areas in a character table. So symmetry operations. These are the characters. Okay, symmetry operations. Irreducible representations. And here they are said to be Mulliken symbols. The irreducible representation, which are said to be Mulliken symbols, which is designated by Mulliken symbols. The irreducible representations. And here this is, okay, this is Cartesian coordinates of rotational axis. Okay, Cartesian coordinates. Okay, then of rotational axis. Then these are the binary products. Binary products. So here it will be linear functions and rotational functions. So this is, and this will be the point group, and these are all the symmetry operations. Okay, so this will be the symmetry operations or elements. So we have done with the constructions of the character table for C2v point group. Hope you all understood. So let us see for C3v point group in the next presentation.